In this video, we are going to take a look at Unit 7, Lesson 7 practice problems. So in this diagram, it says ABC is shown with its incenter at D. So remember, the incenter is the center of the inscribed circle. So it touches each side at one point, which we can see those labeled at F, G, and E. So these dotted lines are all radii of that circle. And so it says the inscribed circle's radius measures 2 units. So every one of these dotted lines here is 2 units. Then it says the length of AB is 9 units. So let me get that on here. So AB, so this segment here is 9. BC is 10 units. So over here, this one's going to be 10. And then AC is 17 units. All right, so then it says, what is the area of triangle ACD? So triangle ACD is this one down here. So ACD, I'm just going to draw all of it pink. So we're looking at this triangle. So to find the area of a triangle, remember that you do base times height divided by 2. And the base here is 17. And remember that the height, because the incenter is the distance to the side, so this length right here, this radius is 2. We also know it's the height of the triangle because it's perpendicular to these radii that are labeled are perpendicular to each side. So the height of that pink triangle is 2. So we end up with base 17 times height 2 divided by 2. So those 2's will simplify out, and we will just get the area is 17 units squared for this pink triangle. Then it wants us to find the area of the entire triangle. So we could do this, we could extend this same idea to these other triangles created. So we can kind of look in at this green triangle. That base there is going to be 9. And again, this is the height, and that's 2. So we'd be able to find the area of the green triangle by doing 9 times 2 divided by 2. So 9 times the height 2 divided by 2, which again is going to cancel those. So this green triangle is going to be 9 units squared. So we've got the pink triangle is 17 units squared, plus now we know the green one is 9 units squared, and then we could reason that that blue one is also going to be 10 units squared because we'll do 10 times 2 divided by 2. And then just add all of those together to get the total area as 36 units squared for that full triangle. Number 2, triangle ABC is shown with an inscribed circle with a radius of 4. So all these dotted lines are 4, which is labeled. The inscribed circle is tangent to side AB at G. The length of AG is 6 units. The length of BG is 8 units. What is the measure of angle A? So we want to find the measure of this angle here. And remember that the incenter is formed by the angle bisectors. So if I connect A to D, that actually cuts angle A directly in the middle or directly in half. And the reason I want to do that is that then this radius here to this tangent line, this is going to be a right angle. So that gives us a right triangle here. So we can see this right triangle. And if you look at your answer choices, they use inverse trig. So we needed a right triangle somewhere in order to get to our trig functions. So if we take a look at this angle here, we could find this angle by doing tan inverse. So we could do the tan inverse of the opposite side, which is 4, over the adjacent side, which is 6, should give us just that little half of angle A. Now, 4 over 6 isn't one of our answers, but if we simplify 4 over 6, that simplifies to 2/3. So this is this little half of the angle, and then the other half of the angle would be exactly the same amount. So we would have 2 of these to equal the full angle. And remember that tan inverse and arctan are the same thing. So B is our answer. Number 3, construct the inscribed circle for the triangle. So that means that we're going to need to find the incenter. So we're going to need to construct the angle bisectors for each side. For each angle. So the angle bisectors. And the way you do that is by opening your compass, drawing a mark through the ray on either side, and then drawing a circle from each of these intersection points. You can open it to the width here, which will guarantee that they cross. So then from that intersection point to the other intersection point, and then you can connect these, connect the vertex through the intersection. That'll get you the angle bisector. And then repeat this for at least one of the other angles. If you do it twice, you should find the incenter. So let me go across the angle so it marks it twice. Okay, then open up to the width here, and then draw a circle. Move over to the other intersection with the side of the angle, draw another circle. And then you can draw your angle bisector in, connecting the vertex through that intersection. And then we just want to make sure that our angle bisectors cross each other, so you can extend it if you need to. And then that would be our incenter. Now, for the incenter, you also need to figure out the radius by connecting a perpendicular line to one of the sides. So from this incenter, you can either find the perpendicular line to AC, AB, or BC. So I am going to find the perpendicular line to BC. And remember, you do that by setting your compass on the point. And then you need to draw an arc that crosses the line, crosses the line you're trying to go perpendicular to. Okay, so I'm going to do this. So it crossed down there. Then at that intersection, okay, you're going to make, you need to make two circles from that intersection. So you can open it to the width to make sure that they cross. As long as you draw 2 circles that intersect, that's fine. Okay, and you don't even have to draw the full circle. You just want them to intersect down here. So I've got from this mark, now I'll move to the intersection over here, draw it again, and then connect the point, okay, to that intersection. I'm going to do this dotted because we're just trying to get the perpendicular line here. Okay, so I'm just going to draw it through. Now the point of that perpendicular line was to get the radius of your inscribed circle. So I only really want to the edge of the circle to open and draw my circle in. Okay, so that will tell me where I open my compass to in order to get the inscribed circle. So we'll open it to here, and then you should be able to draw in the circle. Now mine's a little bit off from the warped kind of screen, but if you do it correctly, you'll get a circle that touches each side. Number 4, point D lies on the angle bisector of ACB. So this is your angle bisector of ACB. And then E is on the perpendicular bisector. So let's do this. Of AB. So here's AB, and then E is on the perpendicular bisector of that segment. So what can we say about these points in relation to the sides and the vertices. So for point D, okay, we know that D is on the angle bisector of those orange ones. So then we can say that point D, let me type this out because it'll be easier. So point D is the same distance from AC as it is from BC, since those are the sides of that angle that it's bisecting. So D is equidistant from the orange sides. Okay, and then what would we say? So that's for the side. So it says sides versus vertices. So for the sides, we can say that. And for vertices, we can't say exactly how far it is from the vertices. There's nothing to help us with that, but E is actually equidistant from A as it is from B. Since it's on the perpendicular bisector, that's equidistant from the endpoints. And D is on this side of E. So D is closer to A. So D is closer to vertex A or angle A, point A, than it is to point B. And that's because we know E is equidistant from them. So then if we talk about E, so we just did a little bit. So for the sides, we'll leave that for a second. But vertices, we know that E is the same distance from A as it is from point B, since it's on the perpendicular bisector, equidistant from those endpoints. And then for the sides, now again, we know D is equidistant. So we know this whole line is equidistant from both sides. And E is on this side of that line. So E is closer to this side, BC, than it is to AC. So E is closer to BC than it is to AC. Number 5, construct the incenter of a triangle. So if we're just constructing the incenter, we're going to do similar to what we did a couple problems ago, except for we don't actually need to construct the inner circle. So we will just construct a couple angle bisectors. So I'm going to cross the side here, open up or go to the intersections, and then open up to the width of the intersection. Draw a circle. Okay, move over to the intersection, draw a circle. And then when you connect those intersections, you'll have the angle bisector. So we'll go here through the intersection. There's one angle bisector. We'll repeat this on one of the other angles, doesn't matter which one. And again, you can do all three if you would like, just to make sure. So I'll draw an arc that crosses both sides. Then I'll open up to that width and draw. And it doesn't matter if you open to the width, they just need to intersect. When you draw these two circles from each intersection, they just need to intersect each other. And then you can connect vertex A through the intersection, and you'll get another angle bisector. And then where those angle bisectors cross is your incenter. So here would be your incenter. Again, you can construct it of C if you want to. Number 6, the angles of a triangle measure 30, 40, and 110 degrees. Will the circumcenter fall inside the triangle, on the circle, or outside the circle? Since it's an obtuse triangle, the circumcenter is going to be outside of the triangle. Number 7, the images show 2 possible blueprints for a park. The park planners want to build a water fountain that's equidistant from each of the corners. Okay, the corners in this case being the vertices. Is it possible for either park? Explain or show your reasoning. So if we could find a point that's equidistant from all of these corners, we could draw a circle, okay, from the point that would hit each of these points. So what we're really looking here is this a cyclic quadrilateral? So we want to look at those opposite angles and see if they total 180. So in this first park, these do not. So we will not be able to draw a circle that touches all 3 points at the same time. So it is not possible for park A. Park B, we can look at the angles that are across from each other or not next to each other. So 105 plus 75 does equal 180, so that's good. And then 133 and 47 also equals 180. So this is a cyclic quadrilateral. So we could draw a circle that hits all 4 points at the same time. And the center of that circle would be where we would put the water fountain. So this one you could. All right, number 8 says we've got the triangles at these different vertices. So I'm going to go ahead and graph this. And we want to find where the medians intersect. Again, you can do this other ways. I just prefer graphing it. So let's go ahead and plot these points. So the points are at -8, 2, 2, 1, 2, 3, 4, 5, 6, and at 10, 2. So if we connect these, we'll have our triangle. And then the median are the segments that connect one vertex to the opposite midpoint. So I'm going to find the midpoint of this bottom segment. And you could literally just count this and go in between because it's a flat segment. So you could just count how long it is. Okay, it's a total of 18 segments long. So you could count 9 to the midpoint. You can also add the x's together and divide by 2 to find the middle of them. So -8 plus 10 is 2, divided by 2 is 1. So that would be our x coordinate. And then we know the y coordinate is 2. So that midpoint is going to be at 1, 2. And then the median, again, connects the vertex to the opposite midpoint. And then your medians cross to create this 2-to-1 ratio on this segment. So we could find the other medians, like we could, figure out the midpoint here and then connect this to the midpoint. However, this segment doesn't seem to have any other integer points on it. So that's still not going to allow us to just count it. So what we're going to want to do here is take this segment. So this is the point 26, and this is the point 1, 2. And we're going to want to split this segment, okay, in a 2-to-1 ratio. And so I'm just going to call this point A and this point B. So we want to take AB and we want to find this point that is a 2-to-1 ratio away from A and B. So we want it to be closer to C. So when we're doing weighted averages, there's 3 total parts that we're splitting it into. And we want the point to be closer to B. So we're going to do 1/3 with A, and we're going to do 2/3 with B, so that that this new point is closer to B. So if I do 1/3 of point A, and point A is the point 26, and I do 2/3 of point B, which is the point 1, 2, this will find me the new ordered pairs for a point that is splitting this segment up or partitioning it into a 2-to-1 split. So we'll do 1/3 of 2, which is 2/3, 1/3 of 6, which I'm just going to leave it as thirds since I'm going to be adding it to this other piece over here. And so I'm going to want common denominators. So 2/3 of 1 is 2/3, 2/3 of 2 is 4/3. And then we'll add these together. So we'll add the x's together. So 2/3 plus 2/3 is 4/3 for our x coordinate. And then 6/3 plus 4/3 is 10/3 for our y coordinate. And so this would be the point that those medians meet at. And if we kind of just look at where we think a 2/3 ratio would be, maybe about here, 4/3 is a little bit over 1 and 10/3 is a little bit over 3. So that makes sense. So 4/3, 10/3 would be the point that the medians intersect at.